Welcome to Click for IB Biology. We're looking at the process of saltatory conduction in myelinated nerves. There's a PDF that you can annotate with your own notes. That's linked in the description below. And as you know by now, there's 10 questions linked into the description where you've also got the answers and you can use those to check your own understanding. So let's take a look at saltatory conduction. Saltation means to jump. And what we're going to be finding out about is that in a vertebrate nerve structure with the Schwann cells myelinating the axon, the nerve impulse, rather than traveling down the entire axon like so and constantly depolarizing at each stage, the action potential effectively is seen to jump to each of the sections between the Schwann cells, which, if you recall, are called the nodes of Ranvier. So this is the only place where you will see the establishment of an action potential. And the influence of this is to greatly accelerate the conduction of nerve impulses along the axon. The axon in cross-section is shown here, but the axon plasm here and around the outside growing here are the Schwann cells. And I've previously discussed the idea that the cell membrane of the axon is like so. Axon plasm is here. And in the development of myelination, the Schwann cells will grow around the outside of the axon, and then they will continue their growth. Can't really draw this particularly well, spiraling around and around and around. And there's an accumulation within the Schwann cell of fat molecules. And in effect, what this does is insulates the region of the axon here. So this region of the axon here is isolated or insulated from the tissue fluid here. And so the depolarizations to action potentials only occur at the nodes of Ranvier. And this longitudinal section here shows one of the nodes of Ranvier here, and there you can see the myelination there and on either side. This is the axon plasm. I'm guessing the nerve impulse is going this way. So how does this actually work? With the action potential at this location here, then the charge difference across the cell membrane, the membrane potential at this location here is of course plus 30 millivolts. And we know that that is going to diffuse forward along the axon of the nerve cell. However, there will be no depolarization of the membrane where there's a Schwann cell, because this is insulating the axon from the external tissue fluid. So the only next location at which depolarization can occur is at the next node of Ranvier. And so if we were tracking the location of the nerve impulse, we're only going to see a charge difference occurring, a membrane potential change here, and then here, and then here. And so effectively, this appears to make the charge jump from one location to another. Although, to be clear, the sodium ions are still flooding down and diffusing down the axon like so. The effect of this is that in myelinated nerves, myelinated by Schwann cells, the speed of conduction can be as high as 100 meters per second. Whereas if it's necessary without myelination to depolarize continuously along the axon, this reduces the speeds, perhaps even to a maximum of approximately 10 meters per second. And this is one of the key features of the rapid nerve impulse conduction that one finds in vertebrates. Its myelination is a key feature of the development of connections within brain tissue. And it, in fact, also leads to the classic idea of where the myelin is like this, it has a white appearance. And this is a phenomena that we will return to when we're looking at the structure of the spinal cord in pain reflexes. So myelination leads to saltatory conduction, with depolarization only occurring at the nodes of Ranvier, and this greatly accelerates the impulse transmission. So a chance to subscribe to the channel. Data suggests that only one in 4 people do actually subscribe. I'd really appreciate it if you did, so it's kind of encouraging. Here's a link to the next video, and there's the playlist for your convenience.